parabolic fractional p-Laplace equations. So this is based on some joint work with Professor Karthik Adimurthi and his doctoral student Harsh Prasad. And what we prove in this result is we prove local Holder regularity for the parabolic fractional p-Laplace equation for all p and for all p in 1 to infinity and for all s in 0 to 1. So, so this is an extension of Georgie Nash-Moser theory to this kind of equation. So I will begin by talking about a little bit about Georgie Nash-Moser theory. I will talk about a little bit about the proof of Georgie Nash-Moser theory in the linear case, and I will give some details about the proof which are similar in spirit to what we do in our paper. So let me just talk about what is, let me talk a little bit about what is Georgie Nash-Moser theory and what is its importance and why should we study fractional operators, for example. So Georgie Nash-Moser theory, the main result in this theory is to prove Holder regularity for weak solutions of elliptic and parabolic partial differential equations which have non-smooth coefficients. So in the equation that I mentioned earlier, we can have coefficients here. So we can put some coefficients here, for example, and we only need to assume that the coefficients are measurable and bounded. Of course, ellipticity condition is also required. So those are the only requirements to prove Holder regularity for the solutions. And this is a very celebrated result of Georgie, Nash, and Moser. So the prototype equation is this, minus divergence A of x grad u. And the assumptions on A are only that A, the matrix A is positive definite, it is measurable and bounded. And what is important about this result is this is one of only two non-perturbative theories in the analysis of PDEs. What I mean by that is that most of the other theories in the regularity theory of partial differential equations rely on perturbation. So for example, there is Schauder theory. Schauder theory gives you regularity of the solutions, provided that we start with some regular coefficients. So for example, in Schauder theory, the coefficients A will be from C0 alpha, and then we can get solution U in C1 alpha. And it's a form of perturbative theory, where we get the regularity for U from the regularity for the coefficients. However, Georgie Nash-Moser theory is a non-perturbative theory. And of course, there is another non-perturbative theory, which is the Gering's lemma, the Myers higher integrability for the gradient. So these are known to be the only two non-perturbative theories. So the notion of solutions, of course, as is well known to everyone, it's the notion of weak solutions. So this is the requirement for local weak solutions, that if we test it with phi, then this holds. And one can, of course, one can solve this in the space W12. So what Georgie Nash-Moser theory achieves is a jump from W12 to C0 alpha. So in that sense, it's a very big jump. And in fact, this is the maximal regularity which can be expected from equations which have non-smooth coefficients. So there is an alpha so that the solutions belong to C0 alpha, and then one can always find a high enough alpha for which the solution is not in C0 alpha if the coefficients are non-smooth. So one can construct examples of equations which have non-smooth coefficients for which one cannot do better than C0 alpha. So in that sense, this is the maximal regularity possible for equations which have non-smooth coefficients. And so I'll just mention some features of Georgie Nash-Moser theory which are well known to everyone. So that does not apply to systems of equations. It only applies to single equations, scalar equations. And the relevance, one can think of an important relevance, for example, from the theory of materials science, for example, in homogenization, where we have non-smooth microstructures. I mean, the base case in homogenization theory is when you have jumps in the coefficients. So this theory, DiGeorgie-Nash-Moser theory, in fact, also applies to such situations where the coefficients have no smoothness whatsoever. And also one can think that when one is doing numerical analysis, for example, for certain equations, then one needs to know some base regularity, some basic regularity of the equations, which will determine what kind of discretization procedure one should apply. So in that sense, all of these regularity theories, in particular DiGeorgie-Nash-Moser theory, is important in many areas of analysis. So I'll just give a brief historical timeline quickly. So DiGeorgie, Nash, and Moser independently proved this result, and by completely different methods, in 1956, 1958, and 1964 respectively, by entirely different methods, completely different methods. However, it turns out that DiGeorgie's method is the most suitable for generalizations to other situations. So the theory of Nash and the theory of Moser is not so amenable to generalizations to other situations. These are the guys. And very soon after, Ledyzhenskaya and Uraltseva, they were able to prove Holder regularity for the elliptic p-Laplace equation with non-smooth coefficients. So this happened pretty soon after the result of DiGeorgie, Nash, and Moser. This is Uraltseva and this is Ledyzhenskaya. Then after that, it took almost more than 20 years before Holder regularity could be proved for this equation. So this is the parabolic p-Laplace equation, and Holder regularity for this equation was proved by DiBenedetto in mid-80s. And this required a completely new idea. The other theories do not require this new idea. So DiBenedetto invented a new method called the method of intrinsic scaling in order to study the Holder regularity for such equations. And I will talk a little bit briefly about intrinsic scaling. So that's DiBenedetto. Now coming to fractional equations. So this is the elliptic linear fractional Laplace equation. And DiGeorgie-Nash-Moser theory for this particular equation is associated with these names: Kastman, Sylvester, Caffarelli, Vassar, Chan, Bass, and many other authors. I'm sure I'm missing some names. And then in 2015, DiGeorgie-Nash-Moser theory was extended to the p-Laplace version of the fractional operators. So this is the fractional p-Laplace equation. And Holder regularity for these was proved by Di Castro, Cusi, and Palatucci in 2015 by one method, and by an entirely different method by Matteo Cozzi in 2017. So they use completely different methods. For us, the method of Cozzi was applicable. The method of Di Castro, Cusi, and Palatucci is not has not been implemented for. It's not successfully implemented for parabolic equations, parabolic p-Laplace equations. I'll briefly mention why should we study fractional operators. So on the mathematical side, one can obtain these operators as Euler-Lagrange equations of certain functionals associated to certain energy norms. So for example, for W12 norm, we have this energy functional, and Laplacian, the operator Laplace comes from this energy functional. Similarly, p-Laplace operator, p-Laplace equation comes from this energy functional. So in the same spirit, the fractional p-Laplace operator comes from this functional. And one can see this kind of functional already in trace theory. So for example, this functional can be thought of as the energy norm for certain trace spaces. So for some weighted Sobolev spaces, or Rn plus 1 plus, so the upper half plane. The trace spaces for such some certain weighted Sobolev spaces, they will give rise to such functionals. And if we compute the Euler-Lagrange equation for this functional, one will obtain the fractional p-Laplace equation. So that would explain mathematically how one can generate certain equations for which DiGeorgie Nash Moser theory could be implemented. However, physically we can think of it as a model for nonlinear and non-local diffusion. So the p-Laplace operator is a model for nonlinear diffusion, and now this the fractional p-Laplace it's a model for nonlinear non-local diffusion. One could think of it in these terms, but also in stochastic processes it appears as the infinitesimal generator of semigrooves for some Levy processes. However, I'm not familiar with this this context so much, so I will not speak more about this. So what I will do right now is first I will give some ingredients of DiGeorgie's proof, and because we kind of follow this proof in spirit, so I just want to show how the proof goes. So the most important ingredient of Holder regularity proving DiGeorgie Nash Moser theorem is the energy estimate for the solutions, so which is also known as the Cacciapoli inequality. So this is what is called as the Cacciapoli inequality for the solutions of the equation. So the equation that we started with, minus divergence A of x grad of u, that equation, from that equation one can obtain such an energy estimate. But this is not just a plain estimate, this is an estimate for truncates of the solutions. So one defines truncates of the solutions in this manner. One defines the object u minus k plus, which is the maximum of u minus k and 0. So we're cutting it off at k. So this is how this function is defined, and then this is used as a test function in the equation for which justification can be given suitably, and then one obtains this energy estimate for the solutions. So this is the key ingredient, and of course we need some other important ingredients such as the Sobolev inequality. So there are two steps to proving DiGeorgie Nash Moser theorem. In one step, one goes from grad u is in L2 to u is in L infinity, and this is essentially due to Sobolev's inequality. So what one does is one sets up an iteration, as we know that Sobolev inequality gives us higher integrability for the gradient of u. So gives you higher integrability for u. So using the fact that gradient u is in L2, one sets up a suitable iteration and using Sobolev's inequality, and one can obtain u is in L infinity using that all of this information. So we will assume in this section that u is actually a bounded solution, which comes as part of DiGeorgie Nash Moser theory. And in the second part, what we prove is that assuming that the solutions are bounded, one proves that solutions are actually Holder continuous. So how does one do this? I'll briefly describe. So what one needs is a formulation of Holder regularity in terms of what is called as the oscillation decay. So local Holder regularity is defined in this way. But however, what we will use, what we prove instead, of course, is what is called as the oscillation decay. So what one requires is, one requires sequences of shrinking radii and sequences of numbers omega n, sequence of shrinking numbers omega n. So these are successively smaller and smaller numbers. Sigma is a number between 0 and 1, so sigma raised to n will go to 0 as n goes to infinity. So these numbers are becoming smaller and smaller. And what one proves is that the oscillation on a ball of radius Rn is dominated by omega n. So on shrinking balls, one gets oscillation decay. And these two are essentially equivalent. So one can go from here to here. So indeed, in Georgie Nash Moser theory, this is what one proves. One proves the oscillation decay. So this is also done in an inductive way. So this is done inductively. So if one assumes something at the level n, and then one proves it for the level n plus 1. So in fact, it is enough to do it at one level. So for example, one can show that oscillation in half of the ball of u is less than or equal to sigma oscillation on the full ball, where sigma is some number between 0 and 1. So it is enough in some sense to prove only one stage of the induction process. The rest of the induction steps are somewhat simple, at least in this case. So the equation that we started with, minus divergence a of x grad u, it has some very nice properties. So the equation is translation invariant, and it is also scaling invariant. So if u is a solution, then u plus k is also a solution. And similarly, we also have scaling invariance. So if u is a solution, then u of x divided by r is also a solution. So using these properties of the translation invariance and the scaling invariance of the equation, one can always restrict to the case where r is equal to 1, u is non-negative, and one can also assume that the supremum of u on the ball of radius 1 is 1, and the infimum of u on the ball of radius 1 is 0. So one can do all of this based on the properties of translation and scaling invariance. So we can assume this for now. And the most important result in proving Holder regularity is what is known as the expansion of positivity theorem. And indeed, in our case also, in our case where we prove Holder regularity for the fractional p-Laplace equation, we also prove an expansion of positivity theorem. So this is one of the main steps in proving Holder regularity. What it says is that suppose that we have some measure information for the solution u. So we have some information of this level set. We have some measure type information for the level set of u of this kind. Then you can get some pointwise information for u. So this theorem is basically converting some measure type information on a ball of radius 1 to a pointwise information on half of the ball. So, and to paraphrase, one can say that if the function stays away from 0 in a large chunk of the set, in the sense of measure, then in half of the set, it will remain away from 0 in a pointwise manner. So this is the main aim of this theorem, to convert measure type information to pointwise information. And I will show very quickly how does one get oscillation decay in this case. So one starts with the oscillation of the solution u in half of the ball, which is the supremum of u in half of the ball minus the infimum of u on half of the ball. Then I replace the supremum on b half by the supremum on the ball of radius 1, which I can do because the ball b1 is larger than the ball b half. And then we use the expansion of positivity result, which tells us that this is less than 1 minus c. However, we already know that the oscillation of u on ball of b1 is actually 1. As I said earlier, we are assuming that the infimum of u on the ball of radius 1 is 0, and the supremum of u on the ball of radius 1 is 1. So therefore the oscillation of u on the ball of radius 1 is 1, and therefore this brief step shows that the oscillation in half of the ball is decaying in this manner. So the oscillation decay can be shown very quickly once one has the expansion of positivity theorem. So the expansion of positivity theorem is the main theorem that one needs to prove. And I wanted to mention that this measure type information in fact comes for free. It comes for free in the following sense. It comes for free in the sense that either the part of the solution which is above half, the measure of that set is a large set, is a large number. If this is not true, suppose this is not true, then one can always flip this picture. One can flip this picture in the sense, then one can consider the new solution 1 minus u of x. And then one can get information, the complementary information to this. So in some sense, this information, the measure type information always comes for free. So either this holds or the complementary condition holds. So in some sense, this comes for free, which is something that I wanted to mention. And there are two steps to proving the expansion of positivity theorem. One is the DiGeorgie iteration, which is a statement like this, which is also a statement where measure information is converted to pointwise information. And perhaps the more important sub-lemma of proving the expansion of positivity theorem is what is called as the shrinking lemma, which says that given any eta, we can find a delta such that the part of the solution which lies above 2 delta is controlled like this. So this is a kind of continuity in measure information for the solution. It is saying that if we can control, if we are given the chunk of the set that we want to in here, then we can choose the level. So we can adjust the level of the solution so that we can achieve this measure information. So as I write, shrinking lemma tells us that if you're given a proportion of the set B1, we can find a level such that the part of the function which lies above that level occupies that proportion in the sense of measure. So it's expressing some kind of continuity in measure property of the level sets of solutions. And what this proof requires is something known as the DiGeorgie isoparametric inequality, and I'll mention quickly what the DiGeorgie isoparametric inequality is. But before that, I've just drawn a picture of what it is saying. So what it is saying is that given an eta, we can adjust delta. So I can slide this upwards or downwards so that we can control eta. So given an eta, I can find a delta so that we can get that measure type information. And what the proof requires is the DiGeorgie isoparametric inequality, which is this statement. It is saying that if you have a function u, which is in W1p or W11, for example, then this is what it says, that so it's giving information about the measures of the level sets of the function u. So it is controlling the measures of the functions, the part of the function which lies above k and the measure of the part of the function which lies below L in terms of the measure of the part of the function which lies between those two levels. So we have two levels, L and K, and what this inequality is saying is that the measure of the set where u is above k and the measure of the set where u is below L, these measures, they're controlled by the measure of the set on which u lies between those two levels. So this is also, in fact, a continuity of measure property for functions in W1P. So this inequality is true for any function which is in a Sobolev space W1P. This does not have anything to do with the solutions of an equation. So this is always true. This inequality is always true for such functions. And what is important about this inequality, for example, is that it tells us that functions like the Heaviside function does not belong in W1P. So a function which is 0, for example, for x less than 0, and then equal to 1 for x greater than 0, such functions cannot belong to W1P, and this inequality in fact quantifies that information. Because on the right hand side of this inequality, we're getting the measure of the set where u lies between two levels. So if we had chosen L to be 0 and K to be 1, then this measure would be, for example, 0 for the Heaviside function. So this inequality is not true in particular for the Heaviside function. And so this inequality is in particular a characterization of the fact that functions which are in Sobolev spaces W1P cannot have jumps. They're not allowed to have jumps from one level to another level. And in fact, this is the main difficulty associated to the fractional Laplace equations and even the fractional p-Laplace equations, because as I will tell later, the functions which belong to WSP, so the functions which belong to the fractional Sobolev spaces, they do not satisfy this inequality. And in fact, they can have jumps. So one can find the Heaviside functions in WSP for some S. So I'll mention a little more about this later. So, I just quickly want to sketch the proof of shrinking lemma using this DiGeorgie isoparametric inequality. So in this is the DiGeorgie isoparametric inequality, which is now written for two levels. So the levels that we choose are 1 upon 2 raised to m and 1 upon 2 raised to m plus 1, where m is a positive integer. So this is the information one gets just from the DiGeorgie isoparametric inequality. At this stage, we have not used any of the fact that u is in fact a solution of the equation. Now we will use the fact that u is in fact a solution of the equation in order to control this term. So from the fact that u is a solution, we will control this L2 norm of the gradient in the next step. So I write the DiGeorgie isoparametric inequality again. This is the DiGeorgie isoparametric inequality. This term will be controlled by Katscher-Pauli inequality or the energy estimate, whereas this term, one of the level sets, will be controlled by the measure type information which we started with. If you remember, I mentioned that we have this measure type information to begin with in our theorem. This is the hypothesis of this theorem. So we start with this measure type information. And using this measure type information, we can control this term. So now we're able to control this term using the measure type information, and we're able to control this term using the energy estimate, as I will show on the next page. So the L2 norm of the gradient, this is controlled by the L2 norm of u minus k plus. The L2 norm of u minus k plus. This comes from the Katscher-Pauli inequality that I mentioned earlier. And since u is the function u minus 1 upon 2 raised to m plus this function is less than 1 upon 2 raised to m. So I can very quickly replace this whole thing with 1 upon 2 raised to m times the measure of the ball. So therefore the gradient of the L2 norm of the gradient of u on this set is controlled by this quantity. Now we substitute all of this back into the DiGeorgie isoparametric inequality that I had written earlier. And when we make that substitution, we get this new inequality where the measure of the set for which the function u is below this level is controlled by am minus am plus 1. So am is the set for which u is less than 1 upon 2 raised to m, and am plus 1 is the set on which u is less than 1 upon 2 raised to m plus 1. So I can very quickly write this in this manner. Now this inequality, as you can see, is special in the sense that we have this subtraction term here, which is primed for doing a telescopic sum. So here one can very quickly do a telescopic sum. So now we're going to add both of these sides over a range of integers m. So this is what we do in the next step. The previous inequality, we add it up from m is equal to 0 to some large capital M. Now this is a telescopic sum, so we are only left with these two terms, which again we can control by something. Whereas the term on the left hand side, we can always dominate it by the smallest. We can dominate it from the lower side by the smallest of these sets. The smallest of these sets is in fact a capital M plus 1, and there are m plus 1 of these terms, so the m plus 1 appears here. So let me write this again in the following manner. So now we can write the previous inequality in this manner. The measure of the set where u is below this level is controlled by c upon m plus 1 raised to half. So how do we prove shrinking lemma from this? We can prove the shrinking lemma from this. So let me quickly go back to what the shrinking lemma was. Shrinking lemma says that given in eta, I can find a delta so that we can control the measure of the set where u is above 2 delta. And one can also write the complementary statement for this, which is what we actually, what I have proved here. So now I can choose an m so that this quantity on the right hand side is controlled by eta times the measure of the ball of radius 1. And as soon as we do that, we have the shrinking lemma for the choice of delta given like this. So what I want to mention is that in this shrinking lemma, what we have used is the DiGeorgie isoparametric inequality, which is available for the Sobolev functions in W1P. However, this DiGeorgie isoparametric inequality, this is not available for WSP functions, the functions in the fractional Sobolev spaces. And that is one of the main challenges associated to proving Holder regularity for fractional p-Laplace equation and also the parabolic fractional p-Laplace equation. So I will just quickly mention what are the difficulties associated with proving Holder regularity for parabolic non-local p-Laplace equation or parabolic fractional p-Laplace equation. So as I mentioned just now, the main difficulty in fact is the absence of DiGeorgie type isoparametric inequality. And the reason for that and an indication of that is the fact that Heaviside function belongs to WSP for small enough s. So if for very small s, Heaviside functions will belong to WSP. So in one of the papers that I wrote with Professor Karthik Adimurthi and my fellow student Harsh Prasad is this type of fractional isoparametric inequality. So in one of the papers that we wrote, we have proved this inequality. So this is the fractional version of the DiGeorgie isoparametric inequality, and this is true for all u in WSP. So as you would remember, in the local case, in the case when we were considering functions u in W1P, we only had one term on the right hand side, and that term was this one. So in the case of functions u in W1p, one only gets the first term, but does not get the second term. Whereas the DiGeorgie isoparametric inequality for functions in WSP, there are two terms on the right hand side. And as I mentioned earlier, this ALK is the measure of the set where U lies between the two levels, K and L. Whereas AL plus is the measure of the set where U is above L. So as we saw earlier in the proof of shrinking lemma, what was important was the telescopic sum. And the telescopic sum can be achieved if one has only the term of this type on the right hand side. If one has this additional term on the right hand side, then it is not possible to obtain a telescopic sum on the right hand side, and therefore trying to prove shrinking lemma using this DiGeorgie isoparametric inequality in the fractional case will not be successful, because we do not only have the telescopic sum here, but we have something else as well. So this fractional isoparametric inequality is proved in this paper, which also came out this year. So as I mentioned, we do not have the continuity in measure property for level sets of WSP functions, and we cannot run the telescopic sum as we did earlier. So this is actually an indication of the fact that Heaviside type functions can belong to WSP, whereas Heaviside functions do not belong to W1p. So this is the first difficulty associated to proving DiGeorgie Nash-Moser theory for fractional equations. Let me mention a second difficulty. The second difficulty, yes.
A brief question. So in the last
Yes.
thing where there were like two terms in this analog of this inequality. So if the other thing, since you have like a measure like term of some super level set, which if u is supposed to be bounded in some sense, then this might go to zero, no? Like, or do you do?
Yes, possibly. However, yes, that is possible. Yes.
That won't help. Does it? Doesn't.
Because yeah, we have not been able to successfully use this term in that manner. I don't think that it is enough to have smallness here. One really needs the telescopic property of this term.
Okay. Okay.
So we tried with that, but I think so. One of the ideas that we had was that it may be possible to push this term to the left hand side, because a term of this type is already present on the left hand side. So as you can see on the left hand side, I already have AL plus. So this term here, this is exactly AL plus. So one of the things that we were thinking is whether it's possible to push this to the left by some kind of smallness. But I'm not sure how to do that at the moment.
Okay, thanks.
So this is the fractional version of DiGeorgie isoparametric inequality, which has a jump term. So that this is due to the possibility of jumps in WSP spaces. So another difficulty which is associated, and in fact one should probably say that this is the main difficulty associated to non-local equations. Sorry, this is the main difficulty associated with non-linear equations, not non-local. The previous one that I mentioned, that was the problem associated to non-local situations, and this is the problem which is associated to non-linear equations. So a p-Laplace equation is a quasi-linear equation. It's a non-linear equation, and the problem is that there is what is called as a scaling mismatch between the two terms which appear in the equation. So we have del T u, which is a term which somehow gives us an exponent 2 in the energy inequality, And there is the second term, which is minus divergence mod grad u to the p minus 2 grad u, which gives rise to a term with exponent p. So there are two exponents present in the equation, 2 and p, and it gives rise to a scaling mismatch. More generally, as I mentioned earlier, for linear equations, we had two properties, two very important properties. The equations are translation invariant as well as scale invariant. So we can scale the equations. For example, we can define a new function u of x by r, and it will still remain a solution of the equation. And we can translate and it will still remain a solution of the equation. However, this is not true for p-Laplace equations of the parabolic type. So for example, this can be seen in the energy estimate for the parabolic p-Laplace equation. So this is roughly an energy estimate or a Cauchy-Pulley inequality for parabolic p-Laplace equation. As we can see here, there are two exponents present in the equation. There is an exponent 2 present in the equation, and there is an exponent p present in the equation. And this causes important difficulties in the analysis of these equations. And what DiBenedetto came up with was the method of intrinsic scaling to solve this issue. So what he did was, instead of considering cylinders of the type Br cross 0r raised to p, he instead decided to consider cylinders of this type. So these are cylinders which are scaled in time. So the time interval has been scaled using some parameter lambda. So now when we write the energy estimate, this parameter lambda appears here. And therefore, if one chooses lambda to somehow behave like the mod of u, then the exponents on the right hand side become the same. So if this lambda is like mod u, then these two combine together and they again become a term like this. So this is roughly the principle behind intrinsic scaling, but I will not talk about that today, since I'm talking about the difficulty associated with non-local phenomena, which is that non-local Sobolev spaces do not have a Georgie type isoparametric inequality. Sorry. So this is the problem, the difficulty which was solved by DiBenedetto. And finally, I'll mention the third difficulty. The third difficulty is associated with the presence of a non-local tail term. So in the energy estimate for fractional p-Laplace parabolic equations, there is an additional term on the right hand side, which is called as the tail term. So this is the non-local parabolic p-Laplace equation, which I have written again. And this is sort of the energy inequality associated to the non-local parabolic p-Laplace equation. And we can see very quickly what are the differences from the local parabolic p-Laplace equation, in that this has an additional term on the right hand side, this term, which is called as the tail term. So this issue is related to the fact that this non-local integral is actually defined in Rn. So this is the equation. As you can see, this term, the non-local term, is in the full Rn. And therefore, when one proves the energy inequality, the analysis that one does is that we divide the domain into two parts, the ball cross ball part and the part which is complementary to ball cross ball. And this term that we see, called the tail term, arises from the complement of ball cross ball. And in particular, this is called as the tail term. So this is another difficulty associated to non-local equations, and indeed it plays actually an important role in the proof, because all of the theorems, for example, the expansion of positivity theorem and the shrinking lemma, they do not come in a natural way. What one needs to assume is one needs to assume a smallness condition on the tail. Only then those theorems are proved. And therefore, when one does the induction step, so in proving Holder regularity, we have an induction step. So in the induction step, at each stage of the induction, one needs to prove that the tail remains small in each iteration. So this is a third difficulty associated to non-local equations. But again, this is also not what I will talk about. I will just address the issue of Georgie isoparametric inequality. So this is in fact the theorem that we have proved. Holder regularity for solutions of fractional parabolic p-Laplace equation for all p and for all s uh, in the suitable ranges. And so the Holder regularity comes in such cylinders. So the Holder regularity is proved in cylinders of this type. So in the time interval, there is a scaling like this. And L, this term L, this quantity L, is related to the L infinity norm of U, but it also contains the tail term. So this is the main theorem that we prove, and it is again, as I mentioned earlier, in the linear case, what Georgie had proved. This is proved using an expansion of positivity theorem. So our expansion of positivity theorem looks like this. So in the linear case, what we had was, we had some measure information, and that measure information was converted into a pointwise information. What happens in the non-local fractional p-Laplace parabolic equation is that we do not start with measure type information on cylinders. We start with measure type information on time slices. So we freeze a time slice t naught, and we have measure type information on that time slice, and only from this information one gets pointwise information for a time interval. So one gets pointwise information on a time interval, but it does not come for free, in the sense that one needs to assume a smallness condition on the tail. So this is what we are calling as the tail alternative. So the pointwise information for U does not come on its own, it only comes as a complementary condition to this. So if this is false, then this happens. So the tail needs to be smaller than some quantity. Only then do
Vivek,
we get, yes.
just a second. So
Yes.
it already means that U is continuous or something in time, which
Yes, so yeah, so the continuity in time is of course a feature of uh, continuity in time is of course a feature of parabolic equation. Um,
okay.
um, One gets that since the solution is in L2 of time interval cross H1, and also the derivative in time is in L2 of time interval cross H minus 1, then one can conclude that in fact solution is continuous in time as a function of H1, sorry, as a function of L2. So one gets that the solution U is in C0T cross L2. Uh,
Yeah, thanks.
uh, but also there is another way to answer this question, which is that one can do a regularization procedure, but perhaps that is not appropriate here. Of course, no. Yeah, uh, um, or of course one can work with Lebesgue points, I would think, but perhaps we have
I'm
continuity in
sorry,
time.
I sorry for distracting you with this question. So please continue.
No, that's fine. Thank you. One gets an expansion of positivity theorem like this. And I only want to briefly mention how does one get the so-called shrinking lemma. As I mentioned earlier, we want to prove a shrinking lemma for the solutions given this measure type information on a time slice. So for that, of course, so this is the definition of tail that I wanted to mention. So tail has been mentioned here. So the tail is defined in this manner. So it's a quantity which is on the complement of a ball. Yeah. So so how does one deal with the lack of Georgie isoparametric inequality? And this is associated to a new energy estimate. So one proves a different energy estimate from the usual estimate. And so this is the new energy estimate. So what is new about this energy estimate is that it has an additional term on the left hand side. So this term that we see here, this is an additional term on the left hand side of the energy estimate. And this is what is called as the good term. And in the linear case, this was discovered in fact by Caffarelli, Chan, and Vassar, who proved the Georgie Nash-Moser theorem for the linear equations. So indeed, this term is already present in the work of the so-called good term is already present in the work of Caffarelli, Chan, and Vassar. And this is the term which will actually give us the DiGeorgie type isoparametric inequality for solutions. So as we saw earlier, the DiGeorgie type isoparametric inequality was valid for all functions u in W1P. However, what one can get from this is a DiGeorgie type isoparametric inequality for solutions of such equations. So I guess one should call it good fortune that such a term appears in the energy estimate, which can be used for substituting the DiGeorgie type isoparametric inequality. So why should this help? One can already see from the form of this equation, form of this term. So in this term, there are two factors. So there is a factor W plus, which is U minus K plus, and there is a factor W minus, which is U minus K minus. So U minus K minus is defined as K minus U plus. So U minus K minus is the same as K minus U plus. So there are two opposing terms in this good term. So there are two opposing factors, which is also a feature of DiGeorgie type isoparametric inequality. So in the DiGeorgie isoparametric inequality, on the left hand side, we have the measure of the set U above a certain level and the measure of the set where U is below a certain level, and their product is present on the left hand side of the DiGeorgie type isoparametric inequality. So in some sense, this good term is already giving us something like this. However, this good term is not present for local equations. So this term one cannot get this term for local equations. So this is in fact a feature only of non-local equations, the presence of the good term. It does not appear for local equations. So in the local case, one necessarily has to use the Georgie isoparametric inequality. Not necessarily, but one has to use it. Of course, there are substitutions for it in the local case. So what one does is, so I'll just briefly mention how this goes. So the shrinking lemma is obtained from the good term. So what one does is one starts with the measure type information on a time slice. And this measure type information on the time slice, it can be propagated for future times. What that means is that one can prove, starting from this estimate, this measure type estimate, one can prove that the same type of measure estimate in fact holds for an interval of time. So one can do this. This is not just a feature of non-local equations. This is not just a feature of non-linear equations. This is a feature of parabolic equations. So for parabolic equations, measure type information on a time slice can be propagated for future times for some intervals, so for some time interval. So one uses that measure type information for a range of time for one of these terms, so either for W plus or for W minus, one uses the measure type information, whereas on the right hand side we can control this by K. So as we know, W plus is U minus K plus, so it is below K. So we can replace this with K here, we can replace this with K here. And as I mentioned earlier, there is also the assumption on tail. So that this assumption on tail has to be part of the shrinking lemma. So we assume in the beginning itself that tail is small. So using the information that W is below K and using the information that the tail is small, one can make the right hand side of this inequality small in terms of K, whereas on the left hand side in this good term, for one of the terms, either for W plus or for W minus, one will use the measure type information of this kind. So one can use this measure type information on a lot of time slices. So one starts with one time slice and one can get this measure type information for a lot of time slices. So for one of these terms, we can use the measure type information, and that will leave us with information, a measure type information for example, for W plus. So in this way, one can obtain the shrinking lemma for the case of non-local parabolic p-Laplace equations. And it is all due to this good term, because we do not have the Georgie type isoparametric inequality. So, so in fact, that is all I wanted to mention about this proof. All of these ideas, they're in this paper, in this preprint. So thank you.
Thank you, Vivek, for the nice talk. If somebody has questions, answers, comments, very fast, because we are running out of time. Very fast. Quickly.
Yeah, thank you very much for the talk. Yeah, I think I asked my questions during the talk, so
sure.
I might have a look. It was very interesting, yeah, for me.
Thank you.
Yeah. Anybody else has any comment, anything? If not, I have just a quick, very general question. So,
sure.
How do you see going these two areas, like regularity theory and the homogenization, your earlier area of work? Do you see? And I can see many tools which can be used in homogenization during the talk. Yeah.
Right.
And I also saw a very few latest papers where they are trying to discuss the regularity of the homogenized problem using the regularity in the inhomogenized problem. Okay, are you getting my point?
Yes.
So
yes,
do
yes,
you
yes.
have any such vision now?
No, that is exactly the reason why I joined TIFR Bangalore. My plan was to learn some regularity theory and then to be able to apply it in homogenization. So in homogenization, there is a very well developed regularity theory. So using the fact that the homogenized limit, it's at least in the periodic case, it's an equation with constant coefficients. So therefore, for the homogenized equation, the solutions are extremely regular. They're very, very regular. So that information can actually be transferred to
That
regularity
statement
or
I don't agree with. I don't agree
yes.
with that equation. But anyway, yeah.
So
No, for example, if you know, I think if you have seen the oscillating boundary problems, right? We start with the
right.
H1
Yes.
functions and then we land into the L2 of 0, A1 and H1 in the second variable. So we
Sure.
lose the regularity when we go for the homogenized problem. Yeah.
Yes,
Okay.
yes.
Okay.
So,
But if
no, definitely the oscillating boundaries and all of these, I would say that those are somewhat open in some sense. One does not know
exactly.
what to do in those cases.
Recently, one of our my colleague with Rajesh, and we have a colleague who works in this area. He
Right.
suggested something that we do homogenization, keeping domain in the domain or PDE who has less regular, do homogenization and discuss its regularity based on the homogenized equation.
Yes, but the principle, the basic principle is that one cannot expect more regularity than what is available for the limiting equation. So if the limiting equation does not have enough regularity, then it cannot be transferred to the oscillating solutions U epsilon. So one can only obtain below that threshold, so not more
Yeah,
than
but
that.
so you also agree with me that this area is completely new and open, just opening
Yes,
up.
yes, definitely, yes. I would say for oscillating boundaries, for free boundary problems, if one wants to do
Hmm.
regularity theory in the context of homogenization, then
Hmm.
that would be a very challenging problem.
Yes,
Definitely
yes,
for
I
oscillating
agree.
boundaries.
Vivek, I
I agree.
think
Thank you.
there
Yes.
was I noticed some typo in one of the pages, like where you first showed
Uh,
the fractional Laplacian. There was a principal value.
okay. Is it here?
Yeah, the first one. So I think there's some test function missing in some sense. I don't know if it's
Uh,
intentional.
no, this is the equation, in fact. So
Okay.
this is a function of
You
x.
mean it's the equal to 0 would mean like it satisfies like a harmonic equation or what? What do you
Uh,
want to have?
Uh, so this is the linear fractional Laplace equation. Uh,
Yeah.
so
Okay. I mean, you mean to say it's like Laplace fractional Laplacian equals to 0 or some?
yes, yes. So
Okay.
this is the left hand side is exactly
Mm.
the fractional Laplace operator, the linear fractional Laplace operator. So
Yeah. Okay.
this is just
Okay.
saying that the fractional Laplace operator equals 0.
Okay.
So
Sure. Mm. Yeah.
so this is a function of x.
Yeah. Okay. No, I think I read it wrongly. Yeah. Sorry. Yeah. Okay. Fine. Thanks.
Thank you.
Bye. See
Okay,
you.
so let's thank Vivek one more time for a
Thanks.
nice talk, and see you next time, Vivek, if you can attend the further talks. Yep.
Yes, thank you. Thank you. Thank you.
See you.
Have a
Bye
good day.
bye.
Have a good night, actually. Bye
Yeah.
bye.
Bye.
You have a good day. Yeah. Thank you.
Thanks.
Thanks. Bye.
Bye.